How's that?
Okay, is that better? Yes. Excellent. Right, so welcome everyone. Thank you for coming to Geospatial Visualization Workshop. You know, there's plenty of other topics that you could have gone to. LLMs are very sexy right now, and there's one next door, so I'm very glad that you came to this workshop instead. So what I would like to maybe start with, so this is the repo that we're going to be, that all of the tutorials are in. The link is there. Has everyone got access to that, cloned it, downloaded it, etc.? If not, we can help you with that, but this is where everything's going to be run from. There are some installation instructions further down with Conda. So Conda creates this command. It will install a number of libraries that we're going to use today. And then there's a little script that you can run called checkenv.py in the repository. So it is just here. And if you have installed everything correctly, it should print out a little smiley face, I think. So if we run it, yeah, there you go. So that's just importing all of the libraries, and then if they import correctly, then a little Matplotlib thing will pop up. You could also run it in Jupyter as well, like it doesn't matter. So yeah, has anyone got any problems with that? I can maybe go and talk through the introduction while you guys get set up and get installed. And then if there's any issues, we can take 5 and we can try to install things. Okay, all good? Okay, so yeah, introductions. My name's Adam. I am here from the UK. I originally come from Northern Ireland, and I really enjoy geospatial stuff. I'm joined today by Kelsey, who is going to help with the tutorial. Kelsey's a bit of a celebrity in geospatial. He's the guy who invented GeoPandas, which is one of the libraries we're going to be working with today. So I've embarrassed him. Sorry. But yeah, so if you've got any questions about GeoPandas, he's the guy to ask. He knows it. He knows it inside out. Right. So without further ado, let's get cracking on some slides. They're going to do an introduction slide where I'm just going to go through, I guess, background on me for a few minutes because ego. And then on the actual tutorials that we're going to work through. So we're going to do 3 tutorials today. Third one we might not get time for. It's quite advanced stuff, but it's there. There's a completed notebook in the repository that you can look at if you don't get to that. But the first 2 are basically everything you need to know, I think, about geospatial data viz, and then the third one's the advanced stuff. So the slides, I'm going to go through the slides as slides, but they are also in Jupyter Notebook. So if you want to follow through with the code that I'm showing on the screen, just go into the slides repository and open up the corresponding Jupyter Notebook. So the introduction is just like literally just slides, so background and stuff. But the geospatial data, this is going to be a background on basically a crash course on all things geospatial. So without further ado, let's maybe get started. So geospatial data visualization. Basically, maps. Like, this is what we're going to be making today. We're going to be making lots of like cool, funky maps. This is a map of shipping lanes. This is rivers colored according to their temperature. The whole point of this workshop is to give you all of the skills that you might need if you decided that you wanted to go out onto the internet, find some cool geospatial data, and make a pretty picture out of it. The pretty picture is like a nice end point, but I think all of the skills required to generate this stuff are really applicable and really useful in the geospatial industry, which is, getting very big at the moment because it's getting cheap to put things into space, and that's where most of geospatial data comes from. Cool. So background on me, I wasn't always in geospatial. I did an undergraduate and PhD in chemistry on materials modeling and that sort of stuff. At the end of, like now, what I do is I track ships for a living. So I went from basically tracking atoms in geospatial or in materials modeling simulations to tracking ships from lat long simulations, or sorry, from lat long from AIS data. And like, to be honest, it's not really a big transition because before I was like tracking atoms moving in X, Y, Z coordinates. Now I track ships in lat long. So if anything, tracking ships is a little bit easier. So I currently work for a company called Synmax who do maritime domain awareness. We track ships with satellite imagery and AIS data. I've thrown this up here because Synmax are hiring at the moment. So if anyone is interested in anything that we talk about today and you're interested in possibly pursuing a career in maritime domain awareness or geospatial in general, maybe have a look at the website or give me, drop me a message or go have a coffee with me and I can explain what those jobs are like. I've also written a book, shameless plug, I wrote a book on this stuff. There will be a discount code which I'll share at some point, so please go and buy that if you're interested. Also ignore it if you don't care. So this is what we've already gone through. Make sure you download the tutorial materials. The Git repository has everything you need to be able to complete this. There are a number of data sets that are required for this. However, I have included them all in the repository, so you shouldn't need to download anything. The data that I've included in the repository is downsampled, so the quality is quite low. On laptops, this is a good thing because the full data sets are quite large, so it takes quite a long time to render these images. And for the purposes of a tutorial, that might not be that useful. But for all of the stuff we do today, if you want to go and get the full data sets and experiment and play around with them yourself, this is the list. They're all linked in the repository. So again, please feel free, to go and get those. Libraries, so again, in the installation instructions, here are all the libraries that you're going to need. I think some of these versions are maybe a little bit old. The versioning shouldn't matter, but I've hard coded these just to make sure, because when I developed this, these are the versions that I used. So just to make sure that I know it's going to work, please use these versions. I think of these, the main libraries we're going to work with today are GeoPandas, Shapely, Matplotlib, and Rasterio. I call it Rasterio, actually. Some people call it Rasterio, which I think is probably correct, but each to their own. We'll also do a little bit with GDAL at the end in the third tutorial. GDAL is like one of those sort of legacy Hall of Fame libraries for geospatial stuff. There's lots of stuff. Most geospatial stuff is built on top of it. I think it's useful, and I think it's very useful to include in this, although the code can be a little bit tricky to use sometimes. So again, please download and get those all installed. Okay, on to the actual meat and potatoes of what we're going to do. First tutorial is we're going to look at vector data. So vector data are points, lines, polygons, and we're going to basically be working with line string and polygon data. There's a data set in the repository which is a rivers data set. So this comes from the Hydrosheds project, which is a huge sort of academic project on building geospatial data around river systems and river basins. So we're going to take that data, we're going to do some manipulations to it, and then we're going to make a river map of, I think in this tutorial we're going to do it of Brazil because there's lots of rivers in Brazil, and so the map looks quite pretty. If you want to go and download the full data set, you can make a map of whatever it is that you want, but we'll get something like this. So this is a map of Brazilian rivers, and they're all colored according to the basin that they're part of. So the red one, well, any guesses what basin is the red? Come on, audience participation. Don't just stare at me. What? Correct. Excellent. See, it wasn't so hard. Everyone, you should get involved. Right, second one, raster data. So raster is basically imagery data. So Kelsey works for a company called Planet. They take satellite images of everywhere around the world. This is raster data. So we're going to be working with two raster data sets. One is topography and one is forest cover. So percentage cover of trees basically. And we're going to make we do all of the common sort of manipulations that you'll do with raster data. So masking it, so taking a polygon and taking a chunk out of the raster and then just using that chunk, or reprojecting the data, so taking the original projections of how the pixel coordinates map onto the 2D pixel coordinates map onto a 3-dimensional sphere, essentially. Reproject it in different ways. And then we're also going to combine it with the rivers dataset to make a map of topography in rivers or forests and rivers, so combining all of the different datasets together. I honestly think that those 2 tutorials will probably take up most of the time. However, there is a third one, and that's a forest map, for example. This is the dataset that we're going to be using, or one of the datasets. And then time dependent, there is a third tutorial that we'll go through, which is sort of advanced raster stuff. This is where we're going to be converting between raster data and vector data. So taking a raster and converting it into points, so every pixel into a point coordinate, or taking the rasters and converting them into line strings, so contour maps. I'm sure you've all seen like OS maps where they have the contour lines. We're going to try and make one of those. Or then go to the other extreme and do polygons, so converting the areas to use maybe topography as an example, areas of the same elevation into individual polygons. And this is all be done with GDAL and Rasterio and GeoPandas. So that's everything. And then that's an example map of what you made. So I think this map shows topography as a raster with contour lines on top of that to like make the topography stand out, with rivers on top of that, and then forests on top of that to try and basically to make like something as close to like an OS map as you can get. I think that looks pretty cool. So yeah, we'll be doing stuff like this today. And the other thing as well is we'll be able to, I think the data sets are set up in a way where for most of these you can, if you don't like Brazil, you may not, you can pick another country and do that instead. So yeah, that's a brief background of what we're going to do today. Does anybody have any questions before I go on to the actual course? Nope. Everyone's happy. Okay. So I'm going to do a very quick background on geospatial data. I would maybe encourage you to open up the geospatial_data notebook in the slides directory, where you can follow along. So I'm just going to go through them as slides. But I would encourage you to open them up as a notebook and work through and sort of click through and play around with the content. This is just going to give, I'm going to try and whiz through this in sort of 15 minutes or so. This is going to give just a very brief background on geospatial data. So the vector data that I've talked about, what is that? What does it look like in a coding sense? Like what does a point look like from a programming perspective? Same with a line string, etc. Same with rasters. So what do rasters look like? How do you interact with those from a programming standpoint? And then other concepts like reprojections. So very, very quick background, basically. So yeah, the four, I'll skip out multi-polygons, but the four sort of main things that we'll be touching on today. So points, these are basically a combination of XY coordinates, so latitude and longitude in geospatial terms. Points can have information associated with them. They could be a value, for example, like elevation. You can have a point in time which has elevation. They can just correspond to places. So if you have a map of the world, points would be like cities or towns, villages, etc. Lines, so line strings, sorry, are the next step up. Essentially, they are one or more connections of points. So an example of that would be, actually there is of course a graph here on the bottom left. So this thing in the middle is a line string, so it's lots of points joined together. An example in the real world of that would be rivers, which we'll look at, or roads, or contour lines on a map. Anything which links two points together. And in theory, you can have an infinite number of points along a line string, but in the example I've shown here, I've just done 3. Then there's polygons. So polygons are a plane figure that is described by a finite number of straight line segments. It's a very long-winded definition. Basically, you can have line strings that are joined back together. So it's basically a shape. So I've drawn one here, which is a square. So everything within that is your polygon. All of these things have their own properties, which we're going to look at in a second. I don't think the properties are that important for the concept or for the purposes of this workshop. However, I think it's just useful to know. I've put multi-polygons there, which I think we can ignore. There are concepts called multi-points, multi-line strings, multi-polygons, which are basically collections of these things. You can have lots of different points all in one multi-point data set. There are reasons for doing this, but I don't think it's important for the concept for this tutorial. And then finally, there's rasters. So this mentioned earlier. This is basically a two-dimensional picture as a rectangular matrix of grid or square pixels. Again, that's a long-winded definition. They're images, basically. In the context of this, they're images. Think of like multi-dimensional NumPy arrays with data stored in the X, Y, Z coordinates. That's what a raster essentially is. So this is just an example of points. So this is a map of CO2 emissions, I think, where there are a series of points plotted in like quite high density, and then they're all colored according to the level of the CO2 emission in that point. And you get this like cool map of basically population density essentially. But you can also see like shipping lanes and stuff, which I think is quite cool. But this is like an example, like an extreme example of what you can do with point data from a visualization perspective. Okay, so in terms of programmatically interacting with points, this is what it looks like. I should maybe introduce the library Shapely. So Shapely is basically it's a geospatial library that, well, it is a geospatial library, and it also does like sort of geometry type stuff, which doesn't necessarily relate to what we're doing today. But Shapely is how you define points. So in this example, I've defined a point. The point is at 0, 0. There are a number of properties that you can get from your geospatial data. So area, length, boundary, latitude, longitude. For a point's obviously got 0 area because it is just a point in space. It's got 0 length. It's got 0 bounds. It's just a single point in space. But latitude and longitude are obviously properties that it has. You can take collections of points and we can plot them. So this is what this looks like. So I've created a list of lots of different points. I have then extracted the latitude and longitudes of those points, and I've plotted them just to show you what they look like. This sort of concept of combining lots of different points into a list is, yeah.
So the Shapely library, is that the same library as you use for interpretability? There's Shapely values that you use for emission curve.
I'm not sure actually, maybe. Maybe share an example after, when we start, so in maybe sort of 10, 15 minutes, we'll go into some examples and we can maybe have a chat then. Anyway, sorry, so this like concept of like combining points into lists is or geospatial data into lists is where we go into the sort of GeoPandas stuff, which we're going to talk about in a minute. Okay, so line strings, again, so this is a river map, all generated with line strings. So same sort of pattern as with the previous example. So a line string is a collection of points. So in this case, I have created a line string and it's a list of, a list of basically latitude, longitudes. So 0, 0 and 1, 1. Again, with the previous example, there are properties that you get from these geospatial, from these line strings. Lines obviously have 0 area again, but they have a length. So length is one of the key things that you get from lines. They also have a boundary as well, so an upper and a lower limit in X and Y. And then they also have latitude and longitude associated with them, or X and Y is maybe the correct terminology to use. And then again, of course, you can combine these all into lists. So polygons, this is a river basin data set, which we'll use a little bit later. Polygons are, again, collections of points, essentially, that are all mapped together. So in this case, I've made a polygon which has 3 points in it, and you you can kind of sort of intuitively imagine it as there are 3 points and lines are being drawn between the points and then joined back to the beginning. So this is kind of what it looks like. So this is an example where I've thrown in a lot of different points and lines are being drawn between all of them and then joined up at the end. And this is what you get. You get this map. In terms of, again, so the property stuff, you get area. So a polygon will have an area associated with it. There is a length. So this, I think, corresponds to the boundary around the outside. There are bounds again. So bounds are the upper and lower limit in x and y of the whole sort of span of that polygon. There's a boundary, so the line around the outside, and then it has a center. So there's also a few different sort of geospatial operations that you can do to polygons. What are we doing here? So we're doing an unary union. This is where we're basically combining lots of different polygons into one shape. So on the left here, left plot, there are 4 different polygons. In the middle one, I have joined polygon, these 3 down here, using this thing called unary union, and it takes those, it calculates like what is the shared area of those 3, and then it creates a polygon of those. And I've done the same thing with all of the polygons, but it gives you back basically 2 polygons. One where where all the shared area is joined, and then the one that it doesn't touch. Don't actually think that's that necessary for this tutorial, but I think it's useful to understand that there are operations that you can do by combining the different data sets, or combining data sets into one, merging data sets and the like. Okay, so GeoPandas. Everything I've shown you so far is basically kind of single examples of points, lines, so using Shapely to create these single instances of a geospatial piece of data. One of the really powerful things that you can do is you can then combine lots of these individuals into one, basically into a pandas object. GeoPandas is basically pandas with a special column, and the special column is like a Shapely list. I might be butchering it slightly. The creator is here, so if you want to know exactly how that was done, please grab him and ask. But essentially, you have a pandas data frame, and so you can do all of the manipulations that you would do in pandas, but you've also got a geospatial column where you can do all of those, so all of these operations here, so area, length, bounds, centroid, etc. You can do that and apply that to an entire column within pandas. So you kind of unlock that sort of, I don't know if vectorize is the right word, but you unlock that ability to, instead of doing things on individual pieces of data, you can apply it to an entire pandas data frame. And then you've obviously got the ability to do all of the slicing and all of that sort of stuff, and then you get access to the plotting and things like that. So it's really, really powerful, and we're going to be using it a lot today. So I've just created a couple of different lists of points, lines, and a polygon. And then I'm creating, what am I doing? I'm creating a single pandas data frame, GeoPandas data frame of all of these data types. So I'm taking all of these points, all of these line strings, and the polygon, and I'm combining them all into a single GeoPandas data frame. And annoyingly, I'm actually just going to open up the code so I can print some things. Oh yeah, there's some warnings in this notebook, like I've suppressed them, just, you don't need to worry about that. I'm going to have to run through this, aren't I? So, okay. What I was trying to show here is, so this is a GeoPandas data frame. We have points, we've got lines, we've got polygons. I've tried to do a number of these operations that I showed in the previous slides on individual points or polygons or lines, but now I'm applying it to the entire data set, so to the entire data frame. So area, so we know from previous that, where's our area column? Yeah, we know from the previous ones that lines and points don't necessarily have an area associated with them, but a polygon does. So here we go, we've got a polygon, and we've applied this to the whole data set, and it has calculated area for everything. Same thing for boundary. We've done boundary and we've calculated the boundary for everything. And then same thing for centroid. We've got the center point of, in this case, everything actually. So yeah, this is just to highlight the power of using GeoPandas, because you're able to do lots of things and apply it to large amounts of data. Okay, so where are we now? Yeah, so there's also some other operations that you can do. In this example, I've got 2 polygons that overlap slightly, and you can apply different combinations of the 2, so you can overlay the 2. In fact, actually, I'm just going to skip this because we're not going to use this in the tutorial, but it's useful to have an awareness of the different ways that you can combine polygons into, or the different ways that you can work with polygons by combining them and things like that. So in this example, I've taken 2 polygons, I've overlaid them, and then I've applied lots of different sort of operations to them, and you get out different things on the other side. So you can take the difference. So this is basically or you can take a union, so you can combine the 2 into one. You can take the difference, so you can get the bits of one that are not in the other, and things like that. I don't think it's that important for this topic, so I'm going to skip it. But if you want to talk about it more, just ask me when we go into the examples. And then finally, we're going to go into rasters. So this is one of the data sets that we're going to be working with. We're going to use a library called Rasterio, or Rasterio. First thing, really, you open the data set. Once you've got the data set, you can then work with it. Essentially, it is kind of like a NumPy array. You can open the data, and you have this data set object. There are properties associated with that, so the width, the height, the boundary. These are basically kind of like the XY limit in terms of pixels, or the number of cells, if you will. There's things like the boundary, the coordinate reference system, so how the pixels map onto that sort of 3D planet Earth. But then you can also read, so you can read the data and you can read it into a NumPy array, and then you can start slicing it and manipulating and doing what you like with it. But this is basically what we're going to be. We're going to be doing a lot of stuff with Rasterio and this data set. All right, finally, projections. So projections are how you map geospatial data onto, so geospatial data comes from planet Earth. Planet Earth is 3D, it's a sphere. And then how do you pictorially represent that on a 2D map, essentially here? So this is an example of the Mercator projection. This is, I think, the most common one probably used in North America. It makes Greenland look massive, or much bigger than it should do. But it's one way of doing it. There are other ones. There's this one. That's the Lambert cylindrical. There's this one. I don't even know what that one's by, BIPC. There's this one splits North America in half, that's kind of cool. There's this one, so Stereo. But yeah, there's lots of different ways that you can project the data. Right, I think that is everything. I think it's now time to get into some actual coding, because I've talked a lot and my voice is getting tired. So maybe pause for 5 minutes. Does anyone have any questions on anything I've just said? Would anyone like a few minutes to go through this notebook and ask, would you like me to walk around and just maybe you can grab me if you don't want to shout at me in this setting, or would you like me to carry on? Okay, we got some thumbs up. Okay, fine. Okay, so we're going to go on to the first tutorial. So everything I've said so far, I'm talking for 20 minutes or so, is basically a background. I think that should cover most of conceptually what you need. I appreciate that I've flown through it a little bit quite quickly. So yeah, if you want to grab me and ask questions, please do. But we will go into the first tutorial. It's the first tutorial we're going to make this data set. Or make this map, I should say. So this is a rivers map of Brazil. The data comes from, wait, what's this? I don't know what, so the title's wrong, ignore the title. So the 3 data sets come from this hydro sheds project. So hydro rivers and hydro basins. Hydro rivers is a data set, terabytes of data of individual river lines, or line strings representing rivers. And hydro basins is the same thing, but basins. Lots of actually quite cool work that they did to generate all of this stuff. So please go and have a look at their website and just read about it, because I think it's very interesting. I've put a downsampled data set into the repository for Brazil, so you don't need to go and download this. I think on conference Wi-Fi it might be a little bit much, so it's up to you. The final one is there's a project called Natural Earth. They do lots of they put out lots of sort of open source geospatial data. We're going to use one of these data sets for plotting the boundaries of countries, so polygons representing countries. I'm going to skip through this. So these few slides here are just the process that I use to downsample the data, so that if you guys want to go get the data and work with it on a different example, this is how you would do it. I've included it here so that there is basically a trail. There's a trail of information, so you know how to do what I've done. But I'm not going to explain it. So we're going to start. So in the resources. In resources/data, there is a file called rivers.parquet.gzip. This contains all of the line strings for the rivers of Brazil. I have removed a lot of the rivers. So this line here, ord_flow. In the Hydro Rivers project, that basically refers to it's kind of like a log scale that links to that references the discharge of the river. I've filtered out anything that basically doesn't have any water flowing through, or a tiny amount of water flowing through it, because the data set will literally include dried up riverbeds that have been dried up for years. So I filtered all of that out just to make it, frankly, a usable data set for this tutorial. So what are we doing here? So we're reading the data. So GeoPandas has a read parquet function. We're reading the data set and then plotting it. This, GeoPandas works brilliantly with, and very similar to the way that Pandas works. You can just select your data frame and then just do .plot, and it will plot it. I've added a couple of additional parameters here, so I've changed the line width and I've changed the color. You can do whatever you want, make them red. Nobody said that rivers have to be blue. And actually, in the UK, we've got a real problem with sewage going into rivers, so the rivers literally aren't blue. So I'm using NumPy to basically scale the size of the rivers. Basically what this is doing is I'm creating a line width column. So I want to plot I want each of the rivers to be scaled according to the discharge of the river, so how much water flows through the river. So I think for the context of this, I don't know if I'm not going to explain this because I can't remember how I wrote this, but basically it's a bit of NumPy magic to take to use basically the discharge column. So there's a numerical column in the data set that relates to the discharge. I've taken that data and I can't remember, it's quite a big scale, 0 to whatever, and I've taken that and I've mapped it or scaled it down into basically between 1 and 0.1, upper and lower. In doing that, I'm then using that data to plot the line width. You might need to grab me and explain it, but add print statements so you can see what this is doing. But basically, we're getting a column called line width dist up column, and this is what we're using to plot our line width of the data set. You could also use different color maps, and you can apply a single column. So in this case, I'm taking the column ord_flow, and I'm using the blues color map. And what this is basically saying is, apply a color map to the values within that column, and so you get this sort of cool, plot. So I think we're now on to an exercise. Yeah. So what I want you to do for the first exercise, there's a data source in here called resources data hydro basins South Am. So this is the river basins of South America. So the rivers are so far just Brazil, but the basins are all of South America. So open it, so load the file, have a look at the columns, have a look at the data, and what I want you to do is to generate maps of the different river basins. So there's a column in here called, I think we want Maj name, so this is the name of the major basin of that polygon, and subname, so this is the sub-basin. So like, for example, I don't know how outdoorsy you all are, but like if you ever go into like a big river valley, you'll see lots of little streams that feed into that bigger river system. So subname corresponds to the name of those smaller basins, those tributaries that flow into the main river, and then Maj name is the major name, the name of the major river basin that all of those sub-basins feed into. So what I want you to do is generate these different maps. Colors are relevant, like go crazy and have fun with the colors. So try and make a map of just coloring everything according to the sub-basin name. Do the same thing for major basin name, and then combine the two into one, and do major basin, but overlay the sub-basins on top. I will wander around. So I think we'll take sort of 10, 15, 20 minutes to do this, and then I'll wander around, and Kelsey can wander around, and we can see how you're getting on. Yeah, I've been talking for like 40 minutes, so I think it's over to you guys for a bit. All right, so get cracking. I'll wander around, and then we'll maybe pick this up again in sort of 10, 15 minutes. This might not work. Apparently it will. Just a quick one from me. What I forgot to tell you is, so yes, by all means follow along in the slides. However, where I've put the tutorials is in the notebooks file, or notebooks directory. This is where there are the actual exercises. So a lot of you have been going to the website, like have been trying to find the, where is it? A lot of you have been trying to find this file. Yeah, here. So this is just this comes from the HydroSheds datasets. I've downloaded it, downsampled it, and then I've put a downsampled version into the folder. If you don't want to download the data, you don't need to. You can just use the downsampled version. So go to this notebook and just start from here. This is using the file that's already in the directory, already in the repository that we're working with. If you want to use the bigger data set so that you can try with a different country or whatever, by all means go and do what's here, but you don't have to do that. What I also realized as well is by using the slides, I mean, the answers are in that notebook, but you're cheating yourself if you use the answers, in my opinion. The other thing as well is there's a branch in the repository called complete, where there will be complete examples. again, like you shouldn't, don't use the answers. Try it yourself for a bit. Okay, maybe going to move on in a couple of minutes. So if anyone's got any more questions, just put your hand up now, or yeah, in 2 minutes I'm going to move on. Okay, I reckon it's time to show you the answers. What am I going to do? Just give me 1 second while I run through this. I think my laptop's about to die. No, as in like it's like literally die. Yeah, I don't know why it's taking so long. Yeah, there we go. Okay, that's taking an impossibly long amount of time. All right, so I will go through the answers now, if that's okay. So I'm trying to run through this live on my own notebook, but my laptop, for whatever reason, is not behaving itself, so I'll just do it off of the slides. So the first two examples, so these two on the left, so this is the sub name, so the sub-basin name, and this is the MAJ name, the major basin name. Excuse me. What we're doing, all we need to do, these are the two lines that matter. I've just put in some subplots so that we can see them side by side. But essentially, we call the basins geodata frame, and we do plot, and then we select the column. So this is the column that we want to use to color the different geometries. So you can kind of think of the geodata frame has got a series of polygons in every row, and what we're doing is coloring each of those polygons according to the value in the column. And so on the left, so I'm coloring it according to subname, and on the right, I'm doing it according to MAJ name. And that's all there is to it. Oh wait, have we got some? Yeah, so my laptop is finally caught up. So what you can do as well is you can do sort of like different things. You can change the color map. So does anyone here have a favorite color map? Yeah?
Oh, I had
a different question.
The basin, that doesn't just choose the color though, right? It chooses the geometry also? Because you plotted, because the geometry was different, not just the color, like it plotted the sub-basins. Geometry
So,
was the first one it did.
Sorry, so which one? I'm not sure I understand. So, okay, so
yeah, when you choose the
this one.
major name as opposed to the subname, the geometry is different between those two, right?
No, yes and no. So okay, hang on. Let's just print it so you can see what we're working with. Basins. So this is what the data set looks like. So you're right. So Madge name, so this is a good example. So we've got, for the sake of argument, we've got the Caribbean coast has, where are we? Has 4 or 5 sub-basins within it. All of the geometries are different. What we're doing is, all of those geometries, when I do the plot, it's plotting everything in the data frame. It's not selecting what it plots, it's just plotting all of these geometries. By using column, all it's doing is it's using the value in the column, so all of the unique values within that column, to color the geometries that are being plotted.
Oh, so it's being plotted, it's just coloring, so you can't tell it's being plotted.
Correct,
Okay,
yeah. So in the case of the Caribbean coast, when I do Madge name, all of the geometries that have this name are plotted with the same color. Yeah, so, okay. Whereas, yeah, color map. So the other thing you can do is you can change the color map. So this is just default, so this will probably be like tab 10, I think. Does anyone have any favorite color maps? Yeah? Can you say that again, sorry? Well, I've literally just typed that in now. So I'm doing it live to show you that you can change the color map. You can apply color map to all of the arguments that are used in the top can be used in the bottom. It's just, yeah, I can't remember what it is now, but like, so all of the different, so if you run basins.plot followed by a question mark, it'll pop up with all of the different arguments that you can use within the plot method. So color map is one of them, color, legend, there's loads. So it's all of the different ways that you can style your plot. As we go through this, I'll start to show you more of those. But yeah. So yeah, where were we? Yeah, does anyone have a favorite color map? What? Blues, okay. So there we go, we've changed it. That is really intuitive, I think. Yeah, so color map's one of the things we can change. So that was one of them. I actually think, yeah, we didn't do the third one. So the third one is, so this one on the right where we have, so ignore the colors, I'll go through the colors in a little bit. But in this case, we wanted to plot the boundaries of the sub-basins on top. So if you remember back to the workshop, the second tutorial that I absolutely flew through, you might remember that polygons have a property called boundary. This is the boundary of those polygons. So we can use that in GeoPandas to get the boundaries of all of our geometries, and then we can plot those boundaries on top of our map. So we're taking a polygon data set, we're creating a line string data set, and then we're plotting the line strings on top of the polygons. I'm going to show you what that looks like because, again, like I appreciate that I've maybe flown through that slightly. So what this will look like would be, oh wait, no, I'm not quite right, am I? Sorry, bear with me. So this second line, I'm taking my basins object, I'm getting the boundaries, so I'm taking the polygons in that and I'm getting the boundaries, and then I'm plotting those boundaries. So I'm chaining two arguments together. I'm taking my basins object, I'm first applying a boundary calculation to get the boundaries of those polygons, and I'm then applying a plotting argument to plot those boundaries. And I hope, what color should a boundary be? We'll do black. I hope this works, actually. Problem with live coding is that it's not always that useful. Yeah, there we go. So we can make the line width a little bit smaller. Yeah, so there you go. Does that all make sense? Does anyone have any questions about that? No? Okay, all good. How far did everyone get with that? Did anyone complete it? Couple of hands, good. Excellent. So, okay, so one of the other things you can do, what we're going to do now is we're going to color the rivers. So we have our rivers data set that we used at the start, so you should have all plotted the rivers by now. We are going to take those rivers and we're going to color them according to the basin that they're in. What I've done here is I've produced a list of colors that I like. I can't actually remember where this list comes from. It's been on my laptop circulating around these tutorials for like 4 years now. No idea where it came from. Might have asked ChatGPT to generate like a list of colors, but who knows. So what we're going to do is we take this list of colors, we create a pandas data frame. The pandas data frame has 2 things in it. It's got basin, and that's going to be a list of our major basin names, so the unique major basin names, the major basin names as a list, and this colors list that I've just created. And then we're going to merge that data set, so that colors data set, with our basins, so that our basins will have so to use the Caribbean coast example from earlier, all of the geometries that have the major name Caribbean coast will have a single color in a row beside them. And we can then use that to plot our data, to plot the data set with these colors. So what I'm doing is I'm doing the same thing that we were doing earlier. So our basins.plots, we're plotting the basins geometries. We are plotting the column Madge_name. But now I'm applying a color. So instead of a color map as we were doing it before, I am basically instead of me saying use a color map and scale or pick colors from that color map, I have hard coded a color value in the data frame itself, and I'm passing that to the plot to say color this geometry with this color. And so that's where these colors came from in the example. So when you run through things to here, you will then have I'm just going to run through this live again so I can plot it, or I can print it and show you what we're doing. I think when I was setting this up, I wanted to have everything included within the slides, which meant that not putting print statements in, because Pandas data frames just don't print very nicely in slides. But in reality, actually just printing and looking at the data frame is much more intuitive than me trying to explain it. So when you run through those, what you get is you get your basins data frame that has all of that data, geospatial data that we loaded in at the beginning. It's got the geometries, so the polygons, and it's now got a color associated with each of those individual geometries. So what we now want to do is we want to take the basins data and we want to join it with the rivers data so that the rivers line strings are now associated with a basin and therefore with a color. So when we plot it, we can get these nice like colored maps. What I think I haven't maybe gone through is how specifically to do that. So there is a line in here which I didn't explain. Yeah. To do that, we need to use a method called sjoin. So GeoPandas has got a method called sjoin. This is an example. Don't run this line. Basically, what it does. So this is rivers, and this is. Well, in fact, let's actually do it live because I think it might help. So what have we called rivers? S America rivers and basins. Okay, so this is what we want to run. So this is going to take the rivers data frame and the basins data frame, and it's going to basically find all of the rivers which are inside the basins. And this will give us a data set where our rivers are mapped up to the basins that they're part of, and then we can plot the data from there.
Big picture question that I think I'm
Sure.
missing. I guess maybe in terms of geometries, are the numbers, like how do we know that the geometries, right, like how do I know that you don't have, the world rivers in, I guess what are the coordinates that we call, like the polygons relative to within the geometries for each of these? Because if I'm picturing here, right, you've got to crop in on South America for the basins, but what if I have river data that's across, the whole map? How are they relating? Is that?
So if you had all rivers in the world,
Yeah.
and you just had polygons for a small subsection of the world, how do they relate to each other? Is that?
Yeah, so I guess the coordinates here in these polygons, is this, like everything is, those polygons are always within like some global, like those are a global map reference, or are they like
Well, so-
X, Y?
Oh, so these values here.
Yeah,
Got it. Okay. So I guess I didn't really explain coordinate reference systems. Okay, so in this case, these are just latitude and longitude.
okay.
Longitude and latitude. Yeah. Yeah, so these are just long.
Within a global,
Yeah.
like it is within a whole world reference always, like when you're handling geospatial
Yeah.
stuff. So always within the whole, with reference to the whole globe, but you have filtered down.
Correct. Yes, sorry. Yeah, I didn't really explain that. But yes, that's essentially right. There is a little bit where I'll touch on this in the next tutorial, but basically, yes, there's a thing called coordinate reference systems where the coordinates that you see here are mapped to a certain. So for rasters, it's much easier because rasters is essentially just X, Y points. So if you plotted an image, you've got random pixel coordinates, which are basically X, Y coordinates in a NumPy array. How do those map onto the real world? That's basically what a coordinate reference system does, and this is all built in within GeoPandas. So all of these coordinates that you see here, so 76.95 or minus 76.95, which is this first one, you're right, that's meaningless in reality, but GeoPandas has a built-in reference system to link that to a place in the real world. Does that make sense?
Yeah, I think the thing I was just like, I'm an acrostomist by training, so like every single image has its own X, like in my brain, every single thing has its own XY. It's quite a lot of work to map them to each other if you've got different microscopes taking pictures of, the same.
Yeah, got it.
You actually have a global reference.
Yes.
For everything, and that was the piece that I was missing.
Yeah. Yeah. Okay. Yeah. Sorry. I kind of made a slight mistake in that we're going through like so much content in this that I have just like flown through it and possibly missed a few things. So yeah, if anyone's got any questions like that, like big picture important stuff, please put your hand up and ask because it is really useful. Do we have any other questions before you guys get cracking on the next exercise? No? Okay, so the next exercise is, so you'll need this line, GeoPandas S-join. This is where we're going to combine two data sets. And the exercise will be going from basically this map to this map. So we're going to color the rivers differently according to their basin. Yeah. Again, probably give this one, so it's about 9:30 now. Yeah, 10, 15, 20 minutes working on this. Kelsey and I will be walking around to help out. And then we'll maybe take a short 5-minute toilet break, coffee break, whatever, and then get started onto the second tutorial, which could actually take longer than this one. So anyway, enjoy. I'll be walking around.
Could you put that really important line down?
course. Okay, hang on. Excuse me. Does anybody have any final questions on this before I go through it and then we take a quick 5-minute break? I can come and find you if you've got questions. No? Okay, so let's just go through this final example in tutorial 1. So what we're doing is a spatial join. This is, you can kind of think of this like, I don't know how many of you use SQL or pandas or things like that, but we're basically combining, we're joining together 2 data sets. We're joining together our rivers data set and our basins data set. So what this line of code is doing, this sjoin line, is it's looking for all of the rivers that are in our rivers data set, and it is finding all of those rivers that are within, or joining with them, all of the data in our basins data set that overlap. So if you've got a river and a basin that overlap with each other, all of the information in the basins data set associated with that basin is then basically copied into our rivers data set. So you get all of the information like the name of the basin and the colors that we merged in earlier. That's all then being associated with that river line string. So you can sort of see, yeah, I've printed it up on the screen. So after running it, we have our multi-line string, which is our river, and we have the name of the basin that it's in, and we have the color, which we added in previously.
So then for each of those lines now, the geometry is only the geometry of the rivers. Each row is a river?
Yeah, so
Can you have multiple, no, that doesn't make sense, multiple geometry forms, but like,
you,
what if you want to?
you can, but no.
Maintain together the geometries of different categories within?
You can. So you can have multiple geometry columns. I'm going to have to defer to you on this. I think one of them is the official geometry column.
Right, yeah. If you have multiple geometry columns, only one of them is going to be used by GeoPandas as the geometry. So you can store geometries in another column. You can switch between them and do other things. But the real power is in doing these kinds of spatial joins and combining them in various ways.
Okay. So if, like, for this example, I mean, I guess you're still maintaining your original databases. So you would, once you do this join, you are effectively saying, like, I only want to look at rivers in, like, post-join. You wouldn't try and keep, like, the river geometries and and the country geometries within the same data frame?
I think you can. Well, you can do that, but okay. I guess you're kind of getting into like data management territory, because no, there's interesting stuff. So like, I think you're into sort of data management territory. You can have everything in the one data frame. It might just get a bit confusing. And then, of course, you are switching between geometry columns if you want to get the polygons, or if you want to get the basins, or you want to get the rivers, or you want to get the country, or whatever it may be. I think that gets quite confusing, perhaps. And I mean, from a plotting perspective, you can still do it. I just think, I think it might be just a bit confusing. Do you think you agree with that? Yeah.
Yeah. I mean, for one-off things, we can do all of this, but thinking about how you want to store your data is another question.
Okay. And then we're on to the final bit, which is the plot itself. And this is very similar to what we've done in all of the previous examples. We're setting the color, and we're using the river basins .colors, or the river basins color column as our as the way we're coloring the data. Essentially what that's doing is when GeoPandas is plotting the data, or when when Matplotlib is plotting the data on behalf of GeoPandas, what it's doing is it's taking this line string and it's plotting it, and it's giving it this color. So the line string, in every row there's a polygon, or there's a I should slow down. There is a line string for the river, and there is a color in every row. And when it's plotting it, it's assigning the color in that row to the geometry. And then we've also got the line width, which we calculated way at the start of this tutorial, to color the size of the river. And again, if I just put that on, if I print that, I think that might make it a bit clearer. Yeah, so it's exactly the same principle. This line string will be plotted with this color, and it will be scaled with a line width of 0.1000628. Cool. That's tutorial 1. Any questions? I think what we should do now, we've been going for like 2 hours, which is a lot of time. Might be time for maybe a 5-minute break for you all to go to the bathroom, get coffee or whatever. We'll maybe start back, so it's 3 minutes to 10 now, so we'll start back around sort of 5, 10 past, that sort of time. All good? Good, all right. See you back here in 10 minutes then. Good work? Excellent. Excellent. Okay, good. I'm just gonna go to the bathroom. Okay. Oh yeah, the RC program. That's good. Well, I think it's possibly because the data sets are a bit smaller. So when I've generated these images, I'm using the full data set.
Well, at least the ones I just have the raster. Yep.
raster data. I think we're still waiting for a few people, but just while you're waiting, so we're going to be working on, if you go to the notebooks directory and open tutorial2_rasters, exercise, that is going to be us for the next period of time. We'll see how we get on. I will be going through what's in the slides directory, which has a little bit more information, but when you're working on the exercise, please use the exercise. If you want to refer to the slides for the answers, please feel free. Yeah, yeah, so I've not labeled it particularly intelligently. Yeah, UX is not my strong suit. Okay, I think that looks like everyone's back. All the empty laptops not have people, or maybe not quite. But let's get started anyway. So Okay, we've finished with the entirety of vector data, so all of the GeoPandas stuff, we've done that, that's complete. You could probably have dedicated like a full 4-hour workshop just to the GeoPandas stuff, but this is kind of a crash course in all things geospatial, so we're going to spend some time now working on rasters. As I said before, rasters are essentially imagery, so 2D NumPy array or 3D NumPy array of data in a geospatial context. This is what we will be working on. This first example, we're going to be plotting a forests data set. So the bit of code that I'm showing you here is not in the exercise. I'm just doing this to show you where the data set that you're using in the exercise came from. There is a data set, if you could follow this GitHub link, there is a high resolution forest cover data set from, I want to say 2008-ish, so it's a little bit out of date, but it's quite high resolution and it looks quite good. That's what this map here is. So what I've done, because it's quite large and it can be quite slow to work with on a laptop, for the purposes of this tutorial, I've downsampled it, so I've scaled it down by a factor of, I think, 10, and saved it into the folder resources data downsampled _forest.tiff, and that is the data set that we're going to be working with in this tutorial. Okay, so I'm going to give a very brief background on a couple of different things, sort of concepts when doing sort of raster data and geospatial, raster and geospatial stuff. And then we're going to do a couple of exercises. But the stuff that we'll do here will be applicable for the rest of if we do get on to the next tutorial, it'll be applicable there. So we start by opening the file. So this is so Rasterio is a geospatial library for dealing with raster data. So raster is the data, IO, input and output. So this line, rasterio.open, this is opening the file. And then we do the forest file, so that we've created an object called forest file, which is the opened data set, and then we can use read to read that data set into a NumPy array. So I've just printed a couple of the properties, so it's all of the various NumPy operations can be done on this array, so we can get the minimum, the maximum values. In this case, I think we've got, so 0 to 100. So there's 101 unique values, 0 to 100. So it's basically the forest data is mapped 0 to 100% tree coverage. The actual definitions of what the academics who did this work is in this link. So if you're interested in how they've done it and where those values come from, go and follow that. But for the purposes of this, it's a pretty picture. Let's just crack on. And we'll ignore the transform for now. So much like GeoPandas, Rasterio has a plotting function called show. Excuse me. So I've imported from rasterio.plot, I've imported show, and then I'm showing that data set. So I'm plotting that data set, and this is what it looks like. This is, and I'm using the greens color map, obviously. We could change that if we wanted to. Again, rivers don't have to be blue and forests don't have to be green. One of the problems with this data set, it's not really that important for this tutorial, but I think it's worth mentioning and just sort of showing you how to fix it, is we have, so the zero data value, so basically if a value is 0, there's no forest there. When we plot this with a color map equal greens, every color in that color map is like some tone of green. And so what it looks like when you plot it is you get this sort of greeny, very light green background. And what I'm doing in this next section is I'm basically going to create my own color map, a custom color map, where I'm going to use basically take a white color and put it at where 0 would be in our color map, so that when we plot our map, 0 data values don't have any green associated with them. It's just going to be a white blank background. So how I'm doing that is I'm taking the greens color map. I'm selecting 100 colors. I want 100 colors within this. I then define, I define a white color. So white is just 0000 in RGBA color terminology. And then I'm creating a listed color map. So this is just a way of creating a color map. What you can actually do is if you wanted to create your own color maps, I think this is kind of fun and quite trippy. You can take a load of random colors and you can pass that list into this listed color map, and then you can get out a color map that you can use to then plot other data sets. And it can be quite interesting, I think. But anyway, that's what this code is doing. I'm not going to dwell on it too much because it's just sort of Matplotlib stuff, and you guys can ask me about it if you're interested. But that's what we're doing here. So going forward in this tutorial, whenever I use color map equals new cmap underscore forests and norm equals norm underscore forest, it's just coming from this, and it's defining our custom color map from the beginning. So yeah, as I say, if you're interested in that, just give me a shout and I can explain it to you. So then when you plot it, now we've got a nice white background. And the only green values are corresponding to places where there is forest. The other thing I'm going to bring up now is one of the properties in Rasterio or our geospatial TIFF is this thing called transform. This is basically a way of, it's sort of the internal way of, it basically relates to the coordinate reference system. So to the question earlier, how do we link, if you look at this map, so look at the X and Y scale. Everyone who looks at this can clearly see that this is a world map. So we've got North America, South America, Africa, Europe, etc. But if you look at the values in the X and Y, these are just pixel coordinates, so XY pixel coordinates. There is no geospatial information that's actually coded in that. So if we wanted to plot this alongside our rivers dataset or whatever, it would be functionally impossible to do so because there's no way of linking. We're not actually, there's no geospatial information coded within this map. What we can do though is Rasterio can take this transform, so basically this way of mapping those pixel coordinates onto a geospatial map. We can pass it in using transform, so transform equals forest file. Ooh, that's not what I want to do. Equals forest file dot transform. Now when we look at the X and Y, it's clearly mapped onto geospatial coordinates. Again, going forward throughout this tutorial, that's going to be important. So we always want to be able to map those pixel coordinates onto a real world location. So taking the X and Y, go on.
Was that transform, is that information stored in the metadata in the TIFF, or how is it?
Exactly, yeah. What you can sometimes get is TIFF files that don't have that information stored, and then you've got to figure it out yourself, and that can be a bit of a nightmare. But yeah, you're exactly right. It's in the metadata. Okay, so that's the concept of transform and how you plot rasters. The other thing, there's a couple of other concepts I want to talk about before letting you loose on an example. One is projections. So we did it in the first we did it briefly in the background sort of slides where we looked at the concept of projections. We can reproject rasters, or we're going to reproject rasters. There are a number of different ways to do this. One way is to use rioxarray. Essentially, what you're doing is you're loading the data. So the coordinate references, or the transform that I mentioned earlier, what it's doing under the hood is it's taking that and it's warping it, or it's manipulating it to apply a new projection onto the data set. So when you then replot it, those pixel coordinates that we had before, those are being mapped to a different location. Because that's essentially what projections are. Like if you look at this map here, like these two maps that I've shown here, the underlying data is the same. It's just being put at a different pixel location on your screen, essentially. And that's what we can do with this rioxarray thing. So we load the file in rioxarray, so we can print the projection. The current projection is EPSG 4326. That's like kind of a default in Geospatial. we can then reproject it from a string. So I'm going to do the Robinson projection. There is a list of projections that you can get from that are available, which I'll show you in a second. We then print the new projection, which is this. We then do the transform, so we transform our original raster into our new reprojected raster, and then we just convert some data. So that's what we're doing here. I didn't actually think I'd put an exercise here, but we have. So for now, would you mind going and working on this exercise? What I want you to do is I want you to load the data, so load up the raster, the downsampled forests underscore TIFF, plot it normally, and then reproject it into a new projection, and then plot that. There are a list of projections here. There's a link in the slides. I don't think I've put it. Yeah, so I've not put that link in the tutorial, but if you go to the slides and then go, so for underscore raster data forests, and go down to the exercise thing, there is a link to PyProj, which is basically a Python library which has all of the information about projections built into it. You can take the values in that and use it here. So where it says CRS from string, we can, you can take like different values from that website and plug them in there. Or if you want to just use what I've done, just use the projection equals Robin, you can do that. So yeah, crack on. So, okay, maybe a couple of other things to point out. So forests underscore NumPy, that is the thing that we're going to be plotting. So this is our converted NumPy array. So if you think of, if you basically think of like the original NumPy array, you've got a load of X, Y, Zs with values in them. The values in them have all been warped into a new location or transformed into a new location after the reprojection. And that's what we're going to plot. All of the code that you need to do that should be here, basically. So yeah, this shouldn't take too long, so maybe give you 5-10 minutes, and yeah, give me a shout if you need any help. So one thing I will point out, for reasons that I can't explain, Kelsey might be able to fill us in, not all of the PyProj strings work. You sometimes get errors. So most of them will work, but some of them will just fail. So I tried to do one called the Spillhouse projection, which is basically, well, it's like centers the world on the South Pole, and it fails. So there's a few that won't work. I'm not entirely sure why. So yeah, just something to be aware of. Yeah, like there's no way that will work. Okay, so I think we can move on because that's a relatively simple thing. So, okay, so yeah, I changed my projection. I'm doing the Eckhart projection, I think. Let's have a little look. Yeah, Eckhart 1. I am reprojecting it. I'm getting my forests NumPy array. This is my reprojected array. I'm getting the transform, so the way to map my pixel coordinates onto geospatial coordinates, and I then plot it. So in exactly the same way that we do up here, so show forests, we do our transform, we do color map, we do our norm. I do exactly the same thing here, and we get this map. So this is sort of kind of blends, I know it kind of curves the northern hemisphere and southern hemisphere a little bit. Cool. Anyone have any questions? Hello.
Yeah, the X and Y coordinates didn't adjust the correct latitude.
They did. So when you reproject things, so these units are in degrees. So every degree is about 111 kilometers. This projection is in a unit that I don't know, but meters? Yeah, meters. Okay, so this projection's in meters. So on X and Y, it's basically meters from the equator going up and down. That's a good question. As soon as I plotted this, I saw it. I was like, yeah, that's going to be a question. But that's a very good question. This is very important to consider, actually. So if you're ever doing like geospatial analysis and you want to calculate the distance between things, the projection that your data is in has a massive impact on that. Because if it's in degrees, you're going to get some value out that won't actually make intuitive sense. So if you reproject it into something that uses meters, it'll actually it then becomes like meaningful and useful to you. The other thing as well is you could just be using the wrong projection and think you're in meters, and then the data that you get out doesn't mean what you think it means. But yeah, that's a really good question. Okay, so let's move that down. So I asked ChatGPT to generate a image describing what masking a raster is. And this is what it gave me, which isn't horrendous, if I'm honest. So this is the concept of, so that data set that we just looked at is a global data set. But what if we only care about, so in this case, this example, we care about the forest of Brazil. So basically we care about the Amazon. How do we get a data set that just corresponds to that area? And what we can do is we can take a polygon, so the polygons that we looked at in the previous exercise. We can take the polygon for Brazil, and we can, like conceptually, you can kind of think of it as you have your map, you overlay a polygon on top, and then all of your raster that's covered by the polygon is masked, so cut out, and then that becomes your data set. So this like clipped data set, essentially. And that's kind of what this is showing. I don't think the polygon on the left is the same as the one on the right, but anyway, who cares? It did its best. So first thing we're going to do is we're going to load our countries shapefile. So this is a natural earth data set. And we're going to get a polygon for Brazil. So this is just a little bit of pandas indexing. And then if you plot it, there you go, there's your map of Brazil. And then we do a thing called, let's maybe make that a bit clearer. We then do Rasterio, or Rasterio has got a built-in sort of function for masking rasters, which is what we're doing here. This mapping thing, basically we're taking all of the geometries from our Brazil data frame, and we're turning those into like something that Rasterio can use. That's all that really is doing. So think of it like this. We've got forest file, so the original raster data set. We've got our geometries, so the raster is being set down, the geometries are being overlaid on top, and the data that we get out the other side, so clipped array forests and clipped transform forests, is a NumPy array of our forest data, and the transform, so the mapping of the pixels to geospatial coordinates for that data set. So this is the next exercise. This is going to take much longer, so we can take as long as we need on this one. On this, what we're going to do is there's another data set in the resources directory, and it's called downsampled_topography.tif. So in this example, we've been looking at forests. Now we're going to look at topography. So what I want you to do is I want you to do a number of things. I want you to load the data. So as we've done in the example with forests, I want you to load the TIFF file. I want you to mask that data. So I want you to take a polygon of a country of your choice. Actually, it doesn't matter which country you choose. So in this line here where I've done Brazil df.log df admin == Brazil, you can pick any country you want. I don't know, bigger countries tend to work best because the data is quite sparse. If you go for a really small country, like if I was to do Northern Ireland, for example, it would be like 2 or 3 pixels because it's quite a small country. But you can choose whatever you like. Once you've then done that and you've got your NumPy array of your topography of your country of choice, then generate a color map as we've done up here. So do something sensible. You can do whatever you like. I will show you some examples of what you can do. And once you've done that, then the final step is to plot it. So plot a map similar to this. So 4 things. Any questions? No? Right, get cracking and we'll walk around and give you a hand. Does anyone need any help? Yeah.
show will accept.
Yeah, it'll either take, show works from either two things. It'll either take your array of data along with a sort of a way of mapping the numpy, the data numpy onto the world, or you can just show the raw file and notify the transform the result of the file. In this case, yeah, absolutely right. You just use the array.
So here, this
Would you like a little bit more time, or would you like me to start going through that example? Who would like, okay, hands up if you would like me to show you how to do it. Got a couple. Hands up if you'd like a little bit more time to work on it. So that was a tie. Let's give it 2 more minutes until, yeah, give it another 2 minutes, and then I'll go through the example. Issues.
Do you know why this thing is not going to plot anything? I'm still at the tutorial one.
Okay, so is this on Navari? Yeah, so this line is, I added this particular bit in after Navari was created, so this column isn't in the data. So this isn't going to work in Navari.
Okay.
So just ignore that.
Oh, I see.
Yeah, sorry. Yeah, the rest of it will work fine, but that one will.
Okay,
will
that
work.
makes sense. Okay.
Yeah.
So, and that's it, right?
That's
this,
it.
This was the tutorial.
Yeah.
Finally. Specific coding challenge for the tutorial one, since I was setting up the dependencies.
Yeah, sort of, I guess. Like, there was a couple. We were plotting these.
Yeah.
So plotting the different basins. This is the sub-basins, the major basins, and then combining the two. Whoops. And then there was plotting this. So this is taking the rivers data set and combining it with the basins data set and plotting them all in one. So coloring the rivers according to the basins.
Okay.
That was the challenge. It's a tutorial. It's not a challenge. You don't need to do it if you don't want to.
Yeah.
But all of so if you go to GitHub,
Yeah.
and then go to the complete branch, it's a bit behind, but like it's fine. There are complete solutions
Okay.
in the notebooks directory, which you can use to get started. But I would maybe go to tutorial 2, which is what we're working on now, and try and work your way through that.
Okay.
No problem at all. Okay, that's been 2 minutes, so I think we'll go through that. Okay, so what was the exercise? The exercise was to load the data, mask it with geometry of a country, generate a color map, and then plot the topography data. Did anybody not use Brazil? So did anyone go off-piste and pick their own one? Lots of people. Any interesting ones? I think I saw India, which looked cool. What'd you go for?
Chile's a bad choice because
Yeah. Yeah, Chile doesn't visualize very well because it is just long and thin. Anyone else do any cool ones? Okay, no audience participation, fine. All right, so what I'm going to do is I'm going to show you, I'll show you how to make the color maps first, actually. So there's a color map called terrain, which is kind of like loosely is the sort of map that you can use for plotting like real world maps. 'Cause you've got a little bit of blue, you've got a little bit of green for land, and then you've got the browns going into white for mountains and hills and whatnot. In our example, we don't have, and this is what it looks like. So what I've done here is I've just got the color map, I've generated a map showing you what it actually looks like. The problem with this is that we are plotting a map that doesn't have any water because we're just looking at the land. So what you can do is you can remove the water from the color map. So this line, numpy.linspace within the call to get the color. So what this is doing is, so plot.cm.terrain is getting the color map, so it's getting the colors from that color map. And what I'm doing is I'm getting the colors between like 0.25 and 1, so the top 75% of the color map and ignoring the bottom 25%. So ignoring these blue colors and just taking all of this stuff. And then as I've done with in the previous example up here, I've then just generated a normal color map, and I've set the color white to be at 0 so that all node data will be colored white. Yeah, if you guys want me to go through that in a bit more detail, I can, but I'll maybe move on to the actual bit of the tutorial because that's what we're here for. Cool, okay. So as before, we open the file, so it's called downsample topography. So we open it and we get our topography file variable. We then run the mask function. So we take our topography file and our Brazil geometry, and we get out a clipped array. So I think for the purposes of making this maybe a bit clearer, I'm going to just print this so you see what it is. So this is just a NumPy array. Oh wait, I need to run that, don't I? Yeah. So this is just a NumPy array, 3D NumPy array by the looks of it. And then the clipped transform is, again, like a just a matrix for mapping those, mapping the XY coordinates in our data set onto a real world topography. Now, one thing I'm going to flag here, I have performed this thing twice. Now, the reason I've done this is because when you mask your raster, so if we look at this, you can't have a NumPy array that's not a rectangle, I don't think. And so when you look at Brazil, like Brazil is not a rectangle. So all of this data that kind of sits in and around the actual shape is going to be given a value for no data. So in this case, I've set no data equals 0. However, what can happen is in some countries you'll have like lowlands and depressions, which will have a which will have like, you know, topography of like -20 or minus whatever. And the problem is then when you go to visualize your data set, you will have, if you assume that all values of 0 refer to no data, but there are values within your data set that are less than that, when you go to view it, you will have random patches of essentially white that correspond to no data throughout your data set, throughout your map, because it's maybe difficult to explain it without plotting it, actually. I'm going to plot it to try and show you what I mean, because I think that might be a bit clearer. Ooh, please work. There we go. Okay, so when I've created my color map, basically when you create your color map, you want, so I'm actually going to explain this in more detail because I think it's important. There are two things that I've done here. I've created a color map, we've gone through that. I'm also creating a boundary norm. So what this is doing is it's a way of mapping how your colors, how the colors in your color map map onto real world values. So in this case, I want all of my colors to map between -28 and 1975 in bands of 1. So what this means is, if I have a color map that has, let's make this a bit simpler. If my color map has 100 colors in it, and then we'll say there's 100 colors there. So when I create my color map, I've got 100 colors in it. When I create my boundary norm, it has 100 values in it. What it means is the value 0 will get mapped onto the first color in the color map. If I have the value 33, it will get mapped onto the 33rd color in the color map, and so on. Basically, what it's doing is it's controlling how colors are mapped onto real-world values. So when you go to visualize your data and you've got a topography of 100 or whatever it may be, a value, a color will be provided, will be assigned to that value. It's all maybe a little bit unclear, but hopefully if I plot it, it might make a bit more sense. So yeah, so here I've set no data equals 0, but when I've created my color map, I have created, so what I've done is I want my color map to be the entire span of Brazil's topography. So Brazil, the lowest point in our data set is minus 28 meters, and the highest point is 1,975 meters. So I want my color map to be able to assign colors to all of those values. However, if all of the no data, so all of the data that doesn't actually have anything associated with it, is set to 0, when you plot the map, all of this stuff around has a value 0, and so it will get mapped onto a color in that part of the color map. I've never been able to explain that well. That was another attempt. Does anyone have any problems with that? Okay, vaguely okay? Okay, good. So, but what we then do is if we were to rerun this, so if you see it where I've done print numpy.amin clipped topography, it says minus 28. That's telling you the lowest thing in the data set is minus 28. So if I now set no data to be equal to minus 28 and then rerun it, now our no data is mapped to the lowest value in the color map, which we've set to be the color white. Does that all make sense? Okay, good. Honestly, I've tried to give that explanation in like 20 different workshops, and I struggle with it every time. It's not always simple. So I think that's it. That's what we were asked to, yes, go on.
Is there a way to basically use like a NA or something like that instead of a...
I think you can. You can, can't you?
It depends on the data type. In this case, the data type is integer, so you can't. Right? But if you had a floating point data type, you can.
Yeah. Did you try that, or did you just know that off the top of your head? That's pretty.
Well, this is just in NumPy, right? So that's controlled by the NumPy part of it.
Yeah, I passed the data to a floating pick.
Yep.
Once I wrote it in, and then just assign it.
Nice. Okay. Yeah. So that's probably a better way of doing it than what I've done, if I'm honest. Okay. Cool. So. And then, yeah, so this is just where I plotted the two things side by side. Anyone have any questions on that? So we've got about, let's say, probably about 45 minutes left. Happy to take 5 minutes now to go through questions on what we've just done, or we can move on to the next part of this tutorial. Hands up, you want to move on? It seems like a majority. That's good news. Okay. What I'm going to suggest is, because we're running a little bit short on time, I'm going to skip these slides here, and we're just going to go straight to the exercise. What these slides are about is about how you reproject a masked raster. So before we had a full data set and we reprojected the whole data set. These slides basically explain how you would, once you've clipped it, so now you've got a NumPy array of your data and you've got the transform values to map it to real world coordinates, how you take that data and how you reproject that. It's there. If you want me to go through it, I can do, but I think because we're getting a little bit short on time and I want you all to be able to generate this last map, I think we should move on and just get on to this exercise. So the exercise is taking the raster data that we had in this and the rivers data that we had in the previous data set and plotting them all on the same map. So you can generate a couple of different things. You can take your topography data and you can plot the rivers on top of that, so you can see how the rivers flow through river valleys, because that will show up in the topography. Or you can take the forests, and you can plot the rivers on top of the forests, and you can see how rivers flow around forests. I don't know. So this will require you to load in the data from the previous workshop into this notebook, then process it as you did in the previous example, and then plot it all in one. So you're taking vector data from GeoPandas, using GeoPandas, and you're taking raster data using Rasterio, and you're plotting them all on the same map. And what this will expose to you, hopefully, is how you can use both GeoPandas and Rasterio within like a broader Matplotlib kind of ecosystem. Because in both cases, in GeoPandas and Rasterio, the plotting that's happening is all built on Matplotlib. And so you can get quite clever and you can get quite creative by passing it, by creating your figure and your axes objects, and then you can pass those into these plotting functions. And once you do that, you can then do all of the cool stuff that you can do in Matplotlib, like add labels, color bars, etc. So yeah, have a crack at this exercise. Before we end today, I will walk through these lines of code, but I don't think that needed for now. Cool. And I'll be around for questions. And I think we'll maybe do this for about 10, 15 minutes, and then we can reconvene and I can explain how this all works. And I don't think we'll bother with advanced rasters. I'm just going to go to the bathroom. You're all right. Yeah, of course. Hang on. Didn't mean to show that one. excuse me, what's you're on Slack, and what's your name? I'll send you, there's a couple of lines of code that you need to make that work. So why don't you message, so there's my name in Slack, why don't you message me and I'll reply with the code. So how's everyone getting on with that? Good? Lots of thumbs up. So for the last sort of, I mean, we got about 35 minutes, but I think we can end a couple of minutes early. For the last sort of 30 minutes or so, it's kind of up to you guys what we go through. I'll go through the solution to that tutorial. There is a third tutorial that we won't have time to go through. I think we bit off a little bit more than we can chew with that. You can, I shouldn't have said that actually. What I should have said is there is some take-home homework for you to keep working on this in your own time that I put together. I could quickly run through that as an example, or you guys can just, like, if you've got questions on anything geospatial, you can just, like, myself and Kelsey can walk around for the last sort of 20 minutes and you can ask. It's entirely up to you guys. So yeah. Anyone have any strong feelings? Anyone have anything they want to do? Nope. Okay, yeah.
One thing I've seen and played a little bit around with was like geodata frame, GeoPandas data frame, and then doing like a show thing with like giving you a browser rendition of it, like cover and explore and stuff like that.
Yeah.
And it was like a show like something. And I don't know if that's
So like an interactive plot.
And I found it really helpful to be able to send people as well.
Yeah. Yeah, so everything that we've done here is basically Matplotlib, effectively. Like GeoPandas and Rasterio, they are built, their plotting is built on top of Matplotlib. There are libraries that exist for the interactive stuff, which, like, I think it's probably too much to go into it now, but there are things like, my mind's gone blank, GeoViews? Plotly is a good one, GeoViews is another one. I've never been that into this, so I'm not the best person to ask, if I'm honest. The reason I've never really bothered with this is because I quite like making pretty pictures. That's just my thing. And interactive stuff, like, it's a different thing. But like, you can use libraries like this and you can generate interactive maps. So like, see some examples. Oh, hang on, that looks cool. Where is it? Oh wait, it's massive. Oh, I understand now. Yeah, anyway, point being, there are some libraries that exist for it. GeoViews is one, HoloViews is another. Well, I think GeoViews is basically a geospatial version of HoloViews. I will show you in a minute an example of how to do this in PyVista. There was a workshop yesterday, and myself and one of the guys who ran it converted some of the data that we're using in this tutorial into a file format that PyVista can use, and then you can like play around with the 3D visualization in a Jupyter Lab notebook. I actually will show you that because it is quite cool. What else? The Plotly, someone mentioned Plotly. Plotly would be another one. I think Bokeh as well is probably another one that has some geospatial components. It's like essentially like it basically will come down to you will need some sort of function that can map the geospatial data onto some sort of file format or whatever internal format is these libraries use to then visualize it. So yeah, that's my answer. I'll load up the PyVista example. I'm going to have to use a different laptop for it though, because Windows is not compatible. Yeah.
So,
I was actually, yeah, it's okay. I'll come to you next. Go on.
so I wanted to know that do you have like a live data where you can say like you want to dynamically load weather report or your traditional or dynamically get the traffic data of the airways or something, or weather traffic or any other dynamics on the geospatial data?
Yeah, I mean, that stuff does exist. It's kind of my job, actually, to be honest. You typically don't plot it, though. So, like, typically what you'll do, so, like, there's lots of, that stuff does exist. Like, you can stream data, geospatial data, and it will work in the same way that any other service will work. It's just you process it as geospatial data, whereas in other examples, you'll process it as, you know, whatever. I don't know if any good, so there's actually, so for weather data, there's so much open source stuff if you wanted to go and play around with weather data. NOAA, I think, have a lot of data sets. There are, I can't remember the name now. Actually, that's actually a good plug. So if you, in the Git repository, if you go to my GitHub and go to this Python Maps SciPy 2022 tutorial, this is the last time I did one of these, there is an example in there of where we made, I think, we used some of like open source weather data. Yeah, so there's like a GIF of rainfall over a year. That looks terrible. My skills have come along a lot in 2 years, or 3 years, because I think that looks awful. But yeah, this is the website here. So yeah, NASA Earth observations, that's it. So there's loads of raster data here you can make. There's a fires data set. It's quite sparse, actually. But there's land temperature. I'm sure there's wind, probably. This is all static data. And the other thing as well is it goes back years and years and years. So you can pull all of it, and then you can turn it into movies and GIFs of how things change over time. Was that actually an answer to your question, or did I just ramble on something irrelevant? Yeah? Okay. Sorry, you had a question as well.
Yeah, I had, we're in the weather space as well. A lot of the weather data is not GeoPandas or anything friendly, like grid files or like NetCDS.
Yeah.
I guess do you have any other suggestions on how to plot them nicely, other than like having it run it through like NetCDS and then plotting it later on, or converting it into, like shapefiles, stuff like that.
Yeah.
Using GeoPandas, there's just kind of like a lot of processing to dig it up.
Yeah, I think, so on the first point, grid files, I think GeoPandas can process those.
Certainly Rasterio can read the SDF directly.
Yeah.
It is gridded data. Some of the other, depending on the dimensionality of it, there might be other tools. Xarray is a good one, or if they're generally accessing.
Yeah, what is the NC file format? Is that?
That's
Yeah. So this is an example where I've used Xarray to load it and process it. We're outside of the bounds of the tutorial where I may have, like, this is ages ago I did this, so I can't remember directly off the top of my head, but like we've got Xarray to open the data set, so now you've got your Xarray, data object, and then you can do, what am I doing? Yeah, so what I'm doing in this actually is I'm converting that into a TIFF. So I'm taking because it's essentially loading it's an array, right? It's loads of different arrays. So what I'm doing with this is loading the array loading the data into Xarray, using Xarray to then process that data, and then saving it as a TIFF. And then once you save it as a TIFF, you can then get access to all of the stuff we've done in this tutorial.
Yeah, and then there is actually an Xarray tutorial this afternoon. I don't know if there's space in it.
Yeah, I think there is. I mean, I think these rooms can take a fair few people, so I'm sure we'll be fine. Anyone else? I'm trying to load up an example of PyVista, which might take me a little bit of time. Okay, so talk amongst yourself for like a couple of minutes while I try and load this. Right, okay, cool. Okay. Okay, this is going on to, so I've got issues with, I've got a very old Windows laptop, which I wrote this on, which I couldn't get working with PyVista. So that's annoying. I'm going to change laptops to do this. How do you extend a display? Wait, there we go. Okay, no, I don't have. Okay, it's not mirrored. All right, whatever. I can try and do this. Okay, so what have I done? You can take a GeoPandas. I'll show you the code in a second, but you can take a GeoPandas data frame. So I have got, in fact, I will show you the code. I might be quiet for a second because I look at this. Okay, so you can take a GeoPandas data frame of like polygon data or line string data. So what you can do in GeoPandas is you can code in a Z coordinate to your shapes. So in the case of contour lines, so let's say for the topography data that we were looking at earlier, you can generate contour lines like you would get on like an OS map, and then you can build in a Z component, and the Z component corresponds to the value of the elevation of that line. You can then take that data and you can convert it into I think it's a VTK format, which is what PyVista uses. And then you can use PyVista to plot the data. And so this is difficult to do, actually. Oh my god. Okay, does anyone know PyVista? How do I make this? How do I like? Okay, that's a bit easier. So this is like China, India, the subcontinent, and it's a contour. So I've generated contour lines, and then I've coded in an elevation into the lines, and so you can get these 3D plots of elevation, and then you can explore it. I think, I can't remember your name, but guy in the chap at the back no, to your beside. I think he works on PyVista. Can you nudge him? Hello? Hey. Hey, no worries. You work on PyVista, don't you?
I assisted a little bit with the tutorial yesterday.
So yeah, but to answer, like stuff like this, this can be exported as HTML and embedded in web apps. So yeah, so there, to answer your question from earlier, this is an example of how you could, do this. I think that's quite cool, actually. It's quite trippy, but it's quite interesting. I'll share the code in the repository to do this. In fact, I think it is in the repository already. Let me just check. Okay, anyone got any more questions, or I can finish up? Oh, wait, that's not the right way. I can finish up by going through the final tutorial and explaining how to do it. Okay, cool. I'll do that then. For context, the PyVista example, it is on the Git repository inside notebooks and in PyVista example. So I've just done what you guys did earlier. I loaded up my original data frame. I got a lot of countries that you saw in that example. Loaded my topography data set, clipped it so that it's just of those countries. I generated, that's what I did there. I then used, this is a bit of GDAL code to convert that raster into line strings. I now have a data frame which is line string Z, so there are 3 components now. There is the XY coordinate of all of the different pixels. Sorry, not pixels, points within that line string, and then there's a Z, which is the elevation of how high that line string is. That's the plot there, which in itself I think looks quite cool actually, but anyway. And then this is a function which will convert that into a VTK object, or file, I should say. And VTK is what PyVista, one of the file formats that PyVista uses. This was really quite hard. I tried to use ChatGPT to do it, and all of the LLMs failed because they are really bad at doing new things, and there's just not very much information on the internet about how to actually convert between these file formats. Eventually I found in the dev branch of a now dead Python project, there was a function that did it. I had to just search GitHub for keywords that I thought people might use to do this, and this is the function that I found. So there you go, it's now out in the open again. So yeah, you save that that can then be saved to a VTK file, and then PyVista can load it and generate your map. So yeah, have a play around with that if you're interested. Yeah?
Is there a simple way to just export the geometry, like XYZ coordinates, into a CSV file?
Yes. So GeoPandas is built on top of Pandas, which has a 2CSV export.
So you can just see that column?
Yeah. I think if you just export it to a CSV, the geometry column will just be exported as, when you print it on the screen and it has the thing, it'll just be printed as that. You can't.
Blender, because Blender has a nice, easy way to import CSV files now. If it's XYZ, then you can print files.
Yeah, that's a good point. Yeah, that's a good point as well. I don't know, Kelsey, do you have any thoughts on that?
You'd have to make explicit XYZ columns from the points, but you can do that. Yeah.
Cool. All right, I'll finish up with the final explanation, and then you can all go to lunch, because I'm sure you're sick of listening to me talk after nearly 4 hours. So we'll just run through that. That's all irrelevant. Okay, so basically you needed to repeat what you'd done in the previous exercise. So we used GeoPandas to load in the rivers parquet file. We then scale the rivers as we did in the previous example. So mapping the discharge values between whatever they were before to between 1 and 0.1. And then I've said it a few times now, one of the cool things or useful things about GeoPandas and Rasterio is because they are all built on Matplotlib, you can build your Matplotlib sort of figure and axis objects, and you can plot lots of different, you can interchange between GeoPandas and Rasterio, and you can plot them all in the same image. which is what we're doing here. So we're generating our, we're doing fig ax equals plot.subplots, and then we're doing show. So we're doing the show thing that we've used in this tutorial to plot the, I think in this case it's forests, and then we're plotting the rivers on top of that. In both cases, we're passing in the axes object to tell to tell GeoPandas to tell Matplotlib that that's what it's plotting on, that's the object to plot on. Vice versa, same thing for Rasterio. And so then if we plot that, we should get the image that's shown above here. As I said earlier, my laptop's quite slow at the moment, so this might take a few seconds to run. A long time to run. Did anyone else have this experience? Was it very slow? Yeah? Okay, fair enough. One of the problems with geospatial data is that there is just so much of it. Like Kelsey can tell you, like working at Planet, I'm sure you deal with like petabytes of raster data every day. Yeah. You get into big data very quickly in geospatial. Wait, there we go. And then you can also do the same thing, but this time do it with the topography. And that's what will hopefully be shown here. Which one did, I assume everyone completed this, which one did you prefer, the forest one or the topography one? Shrugs, no, not interested. Okay. Oh my God, this is depressingly slow. There we go. And there is our map, which I think looks pretty cool. Okay, so that's pretty much it. We can end a few minutes early if you like. The third tutorial, which we didn't get time for, you can have as take-home homework. The idea behind it was switching between data sets. The main one really for converting a raster into points can be interesting. I don't think it's that interesting. Converting a raster into line strings I think is really useful because you can make like contour topography maps. And that was basically what the final exercise is for this. So we're going to use GDAL to convert a topography data set into contour lines, which you can see here. And then the exercise was going to be to plot all of the data from all three tutorials on the same map, which is what this thing here is. Yeah, which I think it looks quite cool. One of the things there's a couple of different things that you can do to make your maps look 3D. So you can hill shade. So if you've got a topography map, you can apply hill shading, which is basically where you simulate a light shining in a direction and from a height. And then you can plot, which generates like a secondary raster, essentially, of the shadow, in a way. And then you plot that on top, and it kind of makes your data set look like it looks a bit 3D because it's kind of like, there's shadows in it. Or another thing that you can do is you can plot the contour lines on top, and that kind of simulates shadows in a way. So like if you look at, I've probably got some examples in this repository actually. If you plot the contour lines on top, you'll get, oh, that's annoying. We don't know what they mean. Let's use that one. Yeah, this is a little bit too low resolution to see it, but if you zoom in and if you plot the contour lines and then you sort of zoom in, you can see that the contour lines, when they're really close together, they sort of give you this hill shading effect, and so the map looks quite 3D, which I think looks quite cool. If you do that in, if you did that in the Himalayas, for example, it would look even more pronounced. But like, yeah, looking at this, you can really clearly see like the valleys and how the rivers sort of move through them. And if you do this in sort of high enough resolution, I think you kind of get slowly towards like what an OS map will look like. All done in, like basically all done in Matplotlib, which is, I think, pretty cool. So yeah, that's take-home exercise. Please go and have a go at that. And yeah, I think we can maybe end it there. And please give Kelsey a round of applause as well. Thanks, appreciate it.